a series of the form summation n equals 1 to infinity 1 divided by n to the p, where p is a positive constant, is called a p-series. And we want to know for what values of p will such series converge, and for what values of p will such series diverge. We'll consider two cases. Case 1, p is greater than 0, less than or equal to 1. In the video prior to this one, we showed that any such p-series diverges. In this video, we're going to consider case 2, where p is greater than 1. And we'll show that if p is greater than 1, then the p-series of that type converges. Examples of p-series of that type are summation n equals 1 to infinity 1 divided by n to the 12th, the summation n equals 1 to infinity 1 divided by n to the pi, and the summation n equals 1 to infinity 1 divided by n to the 1.003 power. All these are p-series with p greater than 1, and they all converge. Before we derive the general case for arbitrary p greater than 1, let us look at a series, a specific p-series, summation n equals 1 to infinity 1 divided by n squared. This is a p-series with p equals to 2. And we're going to show that this series converges by using the integral test. And let's recall what integral test says. When we have a series from 1 to infinity of a sub n, and we're going to assume that each term of this series is positive, suppose we can find a function, so let f of x be a function such that 4 conditions are satisfied. First, f is continuous on this interval 1 to infinity, and if the series starts at 2, then the interval we will be looking at will be 2 to infinity. Second condition, the function is positive, that is f of x is positive for any x in this interval 1 to infinity. Condition 3 is that f must be decreasing. So f is decreasing on the interval 1 to infinity. Decreasing means if we graph f, as we move from left to right, the function drops, or the graph drops. The bigger the x, the smaller the f of x, or if we have to, we can take the derivative and show the derivative is negative on the interval. And the fourth condition is that if we plug in a positive integer into our function, f of n produces the nth term of our series. So this is 4n equals 1, 2, 3, 4, 5, and so on. So if we can find such a function that meets all these conditions, then the conclusion of an integral test is that the series summation n equals 1 to infinity a sub n and the improper integral from 1 to infinity of our function f either both converge or they both diverge. Now what this says is that they both converge or both diverge. If they both converge, it does not say that they converge to the same limit. In fact, that is not the case. So let's look at now at the p-series summation from 1 to infinity 1 divided by n squared. If such a function exists, it must be f of x equals 1 over x squared, because we have to have, when we plug n in there, we have to have 1 over n squared as the value of the function, and this is the only function that can do it. So now let's check the conditions. The function is continuous on the interval 1 to infinity. On the interval 1 to infinity, that's because the only value of x for which it's not continuous, not even defined, is 0, and 0 is not in that interval. We plug in any value into this function except 0, it will be positive. And clearly, if we put in anything into the function on the interval 1 to infinity, it will be positive. So f of x is positive on the interval. The third criteria is that the function must be decreasing. We can take the derivative. The derivative of this function is minus 2 over x cubed. It is less than 0 for x in the interval 1 to infinity, so the function is clearly decreasing. Or we can just look at the function and say the bigger value of x that we put in, the smaller the value of the function 1 over x squared is going to be. So the function is decreasing. And then number 4, f of n is 1 over n squared. So this function satisfies all 4 conditions, and this will allow us to use the integral test. So we'll evaluate the improper integral 1 to infinity of 1 over x squared. If this improper integral converges, so does the function. And if it diverges, the function will diverge as well. This is 1 to infinity x to the minus 2, and the integral of x to the minus 2 is minus 1 over x evaluated 1 to infinity. This is the limit x approaches infinity of minus 1 over x, and then minus a minus 1, so plus 1. This limit clearly goes to 0, so we end up with 1. Therefore, the improper integral 1 to infinity f of x dx, which in this case is the integral from 1 to infinity 1 over x squared dx, converges to 1. So what we can conclude from that is that the series, the summation from 1 to infinity a sub n, which in this case is the summation n equals 1 to infinity 1 over n squared, also converges. What we cannot conclude is that the series converges to 1. That is not true. In a more advanced course, you can show that the series summation n equals 1 to infinity of 1 over n squared converges to pi squared over 6. That's its limit and not 1. So it's important to understand that the conclusion we draw from the integral test is if the improper integral converges, the series converges, but it doesn't say anything about the series converging to the same value as the integral. So now let's show that a p-series summation n equals 1 to infinity 1 divided by n to the p converges for any p greater than 1. Now if p is greater than 1, p minus 1 is positive, 1 minus p is negative. So we have to remember that. And now all we have to do is select f of x equals 1 divided by x to the p, where p is any value greater than 1, and we can go with our checklist. This function is clearly continuous. It's not continuous at 0, but it's continuous on the interval 1 to infinity. Function is positive. Plugging in positive value for x will yield a positive value for f of x, so it's positive. For third condition, this function is decreasing. The bigger the x, the bigger is x to the p, so 1 over x to the p will be smaller. We can also take the derivative. The derivative is going to be minus p times x to the minus p minus 1, and this is equal to minus p divided by x to the p plus 1 in the denominator, and this clearly is less than 0 on the interval from 1 to infinity, so this function is decreasing. And the fourth condition, of course, is going to be plugging in n will give us 1 divided by n raised to the power p, which is the nth term of our series. So once again, we can apply the integral test, and we have to evaluate the improper integral from 1 to infinity of 1 divided by x to the p dx. So this is the integral from 1 to infinity x to the minus p dx, and this is x to the minus p plus 1 divided by minus p plus 1. evaluated from 1 to infinity. Let's rewrite this as x to the 1 minus p divided by 1 minus p evaluated at 1 and infinity. Note that because p is greater than 1, this exponent 1 minus p is negative. So by basic rules of algebra, we can rewrite this as 1 divided by 1 minus p, and then x to the negative of the exponent. So this is minus 1 minus p evaluated 1 to infinity, which is 1 divided by 1 minus p, x to the p minus 1. Now remember, p minus 1 is positive, and this is evaluated from 1 to infinity. Now let's take the limit. Limit x goes to infinity of 1 divided by 1 minus p, x to the p minus 1, and when x equals to 1, this is minus 1 divided by 1 minus p. So we look at this limit. Because p minus 1 is positive, x to the p minus 1 will go to infinity as x goes to infinity, and 1 divided by 1 minus p times x to the p minus 1 will go to 0. So this is equal to minus 1 divided by 1 minus p, which is 1 divided by p minus 1. Therefore, the improper integral converges, because 1 divided by p minus 1 is a finite number. The improper integral from 1 to infinity, 1 divided by x to the p, converges, and by the integral test, so does the p series summation n equals 1 to infinity 1 divided by n to the p. Remember, we were considering the value of p to be greater than 1. For more videos, visit www.mathprepvideos.com.